Hello, calculus fans. Let's now turn our attention to surface integrals of vector fields. Let's suppose that we have a vector field f, and it will be continuous, and let's define it on an oriented surface S. Now, I think I should say what we mean by an oriented surface. So basically, this is a surface that has an inside and an outside, as opposed to things like Mobius strips. A Mobius strip, and this would be a good thing to go look up. A Mobius strip is an object that you get when you take a long, thin strip of paper, twist one end, and then glue it together. That does not have an inside or an outside. Fortunately, we are not going to deal with Mobius strips because we only want to deal with oriented surfaces. And let's say that our surface has a unit normal vector n, then the surface integral of f over the surface S is defined to be the surface integral of f dot n. And this second double integral that you see here is the kind of surface integral that we just talked about. This is a surface integral of a scalar field because once you compute this dot product here, you get a scalar function. This integral is called the flux of the vector field f across the surface S. This definition, of course, requires you to have an orientation of the surface, whether it is outward or inward or up or down or something like that. Most often our surfaces will be oriented outward or upward. For instance, a sphere, we're going to almost always orient that outward. Now, we talked about before an interpretation of this kind of a surface integral. It is the amount of fluid that flows per unit time through the surface S, and the field represents the fluid motion. If the fluid motion is in the same direction as the orientation of the surface, then that flux is going to be positive. And if the flow goes against the surface orientation, then the flux will be negative. Let's say that our surface is parameterized by a vector function, r of v. Then we'll just use our normal vector to be ru cross rv, and then we'll scale that down to be a unit vector. That means we get a nice computational formula for the surface integral of f. Now we want to write down a formula for the surface integral of our vector field. We'll use the definition and replace this integral with a surface integral of a scalar field by saying that we'll integrate f dot n, and n is the vector that we just talked about. If we go back to the definition of the surface integral of a scalar field, we have to plug in the parameterization into the vector field and then multiply by the length of ru cross rv. And now the obvious thing happens. After the cancellation, we get this very nice computational formula for the surface integral of a vector field that's through a parameterized surface. Let's run through an example. Let's suppose that f is the field x negative zy, and we want to find the flux of the vector field through the outwardly oriented first octant portion of the sphere of radius 2 centered at the origin. Anytime that you see find the flux, that means that you are looking to compute a surface integral of a vector field. We've talked about the standard parameterization of a sphere. Here's what it looks like, just to remind you. X equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. Or you can think of this as a vector function with components rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. Now we've already computed this, the cross product of the derivatives of r. We get rho squared sine squared phi cosine theta, rho squared sine squared phi sine theta, rho squared sine phi cosine phi. Now in our particular case, rho is equal to 2. We're dealing with a sphere of radius 2, so we can plug rho equals 2 into this parameterization, and we get this. And we know that since we're dealing only with the first octant portion of the sphere, that phi goes from 0 to pi over 2 and theta goes from 0 to pi over 2. If, for example, we were dealing with the entire sphere, we would say that phi went from 0 to pi and theta went from 0 to 2 pi. Now our field was x negative z, y. And so what we want to do is plug in our parameterization, and this is what we get. So our field as a function of phi and theta is 4 sine squared phi cosine theta, negative 4 sine phi cosine phi, 4 sine squared phi sine theta. Now let's compute f dotted with r sub phi cross r sub theta. And if you do all that, you'll get 16 sine to the 4th phi cosine squared theta. And the last thing to do is to evaluate the integral. And if you work all that out, you'll end up getting 3 pi squared over 4. Notice again that our both phi and theta go from 0 to pi over 2 since we are dealing with just a first octant portion of the sphere. Now, one reasonable question is, how do you know that you're getting the right orientation on the sphere? So if you go back and look at the parameterization of the sphere that we came up with and the particular cross product that we took, that cross product points outward away from the sphere. You can verify that by noting that the z component is going to be positive. That tells you that you have the right orientation on the sphere. When you want a parameterization of a sphere and you compute the cross product and you cross it r phi cross r theta, you will get the correct orientation on that sphere. Okay, that's all for now.